right, so our next speaker will be Ty Robinson from NAU, and he will be now talking more, I guess, the instrumentation and how we actually make the measurements to go after the biosignatures that Chada has described. And so he'll be talking about characterization of planets and biosignatures from atmospheric spectra. How do we actually detect life on a planet that is far, far away?
Wonderful. Thank you, Vicki. Good morning, everyone. Can you hear me okay? Good. Thank you. This is going to make me crazy, so I'm going to try to put this into the pocket there, maybe. There we go. Okay, and we got a back and a forward. And does this have a laser at all? It does. Okay. Hi, everyone. I'm Ty Robinson. I'm new faculty at Northern Arizona University. Today, I want to talk to you about characterizing exoplanets and biosignatures from atmospheric spectra. I'm going to answer 4 broad questions in this presentation. I want to talk about what techniques exist for characterizing exoplanet atmospheres. I want to say something about what those techniques, what kind of information those techniques can actually provide to us. I want to get a little bit into the nitty-gritty about how, when you're handed a spectrum of an exoplanet, you can then try to say something physical about the atmosphere. And then the last thing that I want to say that hopefully will dovetail into some of the talks that are coming later today are what are some of the future prospects for actually detecting exoplanet biosignatures. I know this is a very interdisciplinary audience, so I'm going to start at a pretty basic level for a lot of these. Some of this may be review to you if you're an exoplanet scientist. So in that scenario, you have a few options. You can answer all of those emails that have been piling up all week because you've been doing such a good job paying attention to all of the talks. You could enjoy that portion of the talk from behind your eyelids if you really want to, or what I would prefer, you can just nod vigorously through that part of the talk because you're understanding it so well because it's review. I love that kind of feedback. Okay, so let's start with the first question. What techniques exist for characterizing exoplanet atmospheres? I'm going to use a lot of cartoons here to kind of illustrate what we're talking about. So we're going to talk about 3 primary techniques. We're going to talk about exoplanet transits. We're going to talk about exoplanet secondary eclipse, and we're going to talk about direct imaging. For direct imaging, we're going to be talking about both direct imaging in reflected light and direct imaging in thermal emission. Okay. Let's start with transit spectroscopy. So I have a cartoon here of, say, an image of a star. All of this is actually happening beneath the resolution of your telescope. So remember, this isn't actually what we see with our telescope. And I have some outrageously large planet here that is transiting across the disk of that star in a few different colors. And what I hope you can see is that the atmosphere that I have sketched onto this planet actually appears largest or most extended at the blue wavelength and least extended at the red wavelength. And so in transit spectroscopy, you're sensitive to the fractional dimming of light from the host star. And so what that says is that the more extended atmosphere on this side should be blocking out more light from the host star at the blue wavelengths than at the red wavelengths. And so if you were to plot that up as a spectrum, so how much light is blocked as a function of wavelength, or the transit depth as a function of wavelength, you should have something that kind of looks like higher transit depths at the blue wavelengths and smaller transit depths at the red wavelengths. To say a little bit more about that, overall, the scale of the dimming of the host star goes as the radius of the planet squared divided by the radius of the star squared. It's just geometry. Planets are going to appear at larger at wavelengths that correspond to regions of atmospheric opacity. So I'm thinking about things like molecular absorption features. And so if you do detect that a planet is larger at some wavelength than at some other wavelength, that's telling you something about wavelength-dependent opacity in the atmosphere of that planet. And then remember that in transit spectroscopy, you're not actually detecting any photons of light from the planet. You're actually just detecting a lack of photons of light from the host star that have been blocked out by the solid disk of the planet or the atmosphere of the planet. Yep. There we go. Thanks. Oh. Okay, leaving transits behind, let's talk about secondary eclipse. And so in secondary eclipse, you take an observation of the star-planet system. Again, all of this is happening beneath the resolution of your telescope, just before the planet disappears behind the disk of the host star. And then you repeat your observation after the planet has gone into secondary eclipse, so it has disappeared behind the disk of the host star. If you think about it, in this observation, the light that you are receiving is the combined light of the star and the planet, whereas in this observation, you just have the light from the star. So if you take the ratio of those two observations, you would have Fs plus Fp divided by Fs, or 1 plus Fp on Fs, which is the planet to star flux ratio. And so secondary eclipse observations are then sensitive to the planet to star flux ratio for that planet star system. I will say that this works best at wavelengths where the planet is emitting its own light. The contrast there works in your favor. If you think about trying to do secondary eclipse in reflected light, the light from the star falls off as 1 on r squared to the planet, and then the planet presents to you a disk whose size scales as the radius of the planet squared. And so secondary eclipse observations in reflected light should scale as the radius of the planet squared divided by the orbital distance squared. Remember that I said transit scale is the radius of the star squared divided by the radius of the planet squared divided by the radius of the star squared. I don't know any planets that orbit at 1 stellar radius from its host. And so that means that the secondary eclipse in reflected light is always going to be smaller than the transit signal by usually at least an order of magnitude. And so it's a more difficult measurement to go after in reflected light. So let's then focus on thermal emission. Here's my cartoon of a star-planet system in thermal emission, viewed at 3 different thermal infrared wavelengths. And remember, we're going to be talking about the planet to star flux ratio, and so I hope that when you stare at these images, you might be able to tease out that the ratio, the brightness of this disk, and the brightness of this disk is the least in the cartoon. And so if you were to plot this up as a spectrum, you would get something that kind of looks like this. Planet to star flux ratio spectra in the infrared have this characteristic climbing shape, and then superimposed on top of that can be things that look like absorption features, again due to, say, opacity in the planet's atmosphere. A few extra words about secondary eclipse spectra. So first of all, you expect it to roughly scale as the ratio of the emission from the planet to the emission from the star. So something like a black body at some characteristic temperature for the planet divided by a black body for some characteristic temperature of the star. The ratio of 2 black bodies is a wavelength-dependent quantity, and so you expect there to be wavelength-dependent structure in secondary eclipse spectra, regardless of whether or not there are atmospheric features. And so deviations from that wavelength-dependent structure can then tell you about opacity in the atmosphere or species in the atmosphere. And then lastly, let's talk about direct imaging in both reflected light and emitted light. You are probably all most familiar with direct imaging of hot, young exoplanets, where the contrast ratio is working in your favor. The planet is still glowing with its residual energy of formation, and so the contrast between it and its host is favorable for doing direct imaging from the ground. This is the famous HR 8799 planetary system that has at least 4 of these hot, young Jupiters in the system. And a coronagraph has been used to beat down the light from the host star to allow you to see these gas giant exoplanets. And so this is direct imaging in the thermal infrared. Let's talk for a second about direct imaging in reflected light. And so here I have a cartoon again of a planet-star system at 3 different wavelengths, blue, green, and red. Usually, when you're presenting reflected light observations of a world, you divide out the stellar spectrum, because it's the starlight that's shining on the planet that's then reflected and coming to you, the observer. That starlight has its own wavelength-dependent shape and has its own features that will show up in the raw spectrum of the planet, but if you divide out the stellar light, you're then just seeing the features of the planet itself. And so I hope that you can kind of spot that the planet appears pretty reflective here in the blue, met in the green, and then maybe pretty dark here in the red, such that if you were to plot this up as a spectrum, it might look something like this, more reflective in the blue, met in the green, and absorbing potentially in the red. Let's go to infrared wavelengths now, thinking about direct imaging at thermal infrared wavelengths, like for the HR 8799 system that I just showed you. Here, if you divide out the stellar light, it looks exactly like secondary eclipse and behaves just like secondary eclipse. You're viewing the 2 worlds in thermal emission. But because in direct imaging, you're actually separating the light from the planet from that of the host star, you can then actually present the raw flux from the planet. You don't have to divide out the stellar flux. And so then you can imagine that spectrum that you obtain could look something like a black body-esque shape because it's thermal emission with some kind of features superimposed on top of that due to opacity in the atmosphere. Okay, leaving those techniques behind, let's talk about, or leaving direct imaging behind, let's talk again about what these techniques can tell us about exoplanet atmospheres, starting again with transit. So here's a cartoon again of an exoplanet transit. And I'm going to ask the question, what is the additional transit depth caused by the atmosphere on that planet? That is the atmospheric signature. That is what we would want to go after for detecting biosignatures or for understanding the composition of an exoplanet atmosphere. Well, this is just geometry. This atmosphere here is an annulus. And so the area of that annulus, as long as the thickness of that atmosphere is small compared to the radius of the planet, the signature of the atmosphere then looks like area of annulus divided by area of the stellar disk, just geometry. Grade school me would be super impressed with present me for doing geometry. But let's do a little bit of physics. No, that was back. And ask, well, what should we use for the thickness of the atmosphere? Think about that for 1 second. Some physical quantity that you might use for the thickness of the atmosphere. And so here I'm going to propose that a good thing to use is the atmospheric pressure scale height. You get that from taking the hydrostatic equation and combining it with the ideal gas law, and then you find that pressure decreases exponentially with altitude, assuming an isothermal atmosphere. The E-folding length for that decrease is called the pressure scale height, and it is an indicator of heights in planetary atmospheres. So Earth, the thick part of Earth's atmosphere where we hang out and where airplanes fly in is about within 1 scale height of the surface of Earth, and then all the way up to the top of Earth's stratosphere is of order 10-ish scale heights in Earth's atmosphere. So the scale height is a good indicator of the thickness of an atmosphere. It has this functional form, and I'll just tell you what these are. So it has the Boltzmann constant times an atmospheric temperature divided by the mean molecular weight. All of this comes in from the ideal gas law, and then divided by the gravitational acceleration or the surface gravity, which comes in from the hydrostatic equation. So if I plug all of that into the expression up above, you get that the signature due to the atmosphere scales in this way, and I'm now throwing in a little fudge factor here because the thickness of the atmosphere isn't guaranteed to be 1 scale height. It could be several scale heights, or it could be less than a scale height. And so I'm calling that factor X. And so the question I have is, well, where does the wavelength dependence come in this expression? I haven't actually explicitly said anything about wavelength dependence in that expression. Think about it for a second. And so it comes in these factors X here. And so where the atmosphere has strong opacity, it's going to appear larger when silhouetted on the disk of the star. And where it has low opacity, it's going to appear smaller when silhouetted on the disk of the star. And so that fudge factor X is going to have a wavelength dependence to it. Okay, so staring at all those parameters, things that you could then hope to constrain from a transit spectrum would be atmospheric opacity, wavelength dependent atmospheric opacity, something about atmospheric temperatures, atmospheric composition from the, or bulk atmospheric composition, which would show up from the mean molecular weight dependence there, surface gravity, and then planet size. Things you could then infer, given that information, might be something about trace and bulk gas composition due to absorption features, something about aerosols, if they have features that show up in the transit spectrum. You might be able to say something about atmospheric pressure, say through Rayleigh scattering opacity. And then if you combine the gravity and the planet size, you might be able to say something about planet mass, which was a paper by DeWitt and Seeger in 2013. But I will attach the caveat that you can look at that expression and see that there are probably all kinds of degeneracies that are going to be present when you try to make these inferences. So first of all, look at the mean molecular weight of the atmosphere and the gravity right there. I could have the gravity of the planet and double the mean molecular weight of the atmosphere and have the same scale height. And so those two parameters could easily be degenerate unless you have some additional constraint on the mean molecular weight of the atmosphere. Here is a simulated transit spectrum of a planet. This is our Earth transiting across a mid-type M dwarf. So over here is the transit depth, and the scale of the transit depth is just set by the radius of Earth squared divided by the radius of the star squared, and then there are additional bumps and wiggles structure in there due to gases in Earth's atmosphere. On this axis, I'm plotting it as effective transit altitude, which kind of tells you where in the atmosphere you're probing at those different wavelengths. And here's wavelength spanning the near UV out to the thermal infrared on the x-axis. And so you can read off a number of species, some of which are biosignature species. Something that I want to point out, though, is that notice the extremely limited sensitivity that we have to the surface environment in this spectrum. If I go back, if you look at the black line, which includes clouds and refractivity from the atmosphere, we never get down to below about 7 or 8 kilometers from the surface, which is just due to the geometry of transit. You have very long path lengths through the atmosphere, and so even a thin cloud can interfere with your ability to probe to the surface. Furthermore, with these really long path lengths through the atmosphere, even small molecular opacities can start to add up. And so, for example, in the wing of this 15 micron CO2 feature, where opacities are low, you can still block out your ability to sense the surface due to weak CO2 absorption through the pressure broadened wing of that 15 micron CO2 band. Okay, secondary eclipse. And I'm also going to tack on direct imaging and thermal infrared because they're so similar to one another. So what do we think that the shape of a secondary eclipse spectrum might look like? Well, I would argue that it's going to scale something like a black body. So it's going to look like the planetary radius squared times the Planck function. And then all of my radiated transfer mentors are going to pull their hair out right now. But I could say then superimposed on top of that is going to be atmospheric structure, which I'll just lump into some kind of atmospheric emissivity that causes you to deviate away from a black body. And so putting that up at the top of the slide, what are things that we could then hope to understand from a direct imaging in the thermal infrared or a secondary eclipse spectrum? Well, again, atmospheric opacity is going to affect this emissivity term here. You have information about atmospheric temperature because you're viewing the world on thermal emission, and you have information about planet size. On top of that, what are things you could then hope to infer? Well, if you have information about the atmospheric opacity, you can then try to say something about the atmospheric composition, bulk or trace gas. You could try to say something about aerosols, atmospheric pressure. Here you're thinking about long wavelengths, so now I'm not thinking about Rayleigh scattering, but I'm thinking about how pressure broadening impacts molecular absorption features, which can then give you a constraint on atmospheric pressure in these observations. And if you have information about atmospheric temperature, you might be able to get at how the temperatures are changing with altitude or with pressure in the atmosphere, which is the lapse rate. The lapse rate is affected by condensation of species giving off latent heat. So maybe you could hope to go after understanding condensation processes in atmospheres through their impact on the thermal structure. One last thing to point out is that in the geometry of secondary eclipse or in direct imaging, you have pretty much straight down through the atmosphere views, which means that you're sensitive now to deeper levels of the planetary atmosphere than you are in transit observations. So in that way, they're very complementary to one another. Here are some actual direct imaging observations, spectroscopy. There are a few of the HR 8799 hot young gas giant planets plotted here as the flux of the planet as a function of wavelength. A number of different groups have attempted this, and so this plot looks rather messy with everyone's attempt to try to get a spectrum of these worlds. But what I hope you can kind of see is that these look black body-esque and that they're climbing out towards longer wavelengths. These things are about 1,000 Kelvin in temperature, so they should be peaking in their black body somewhere out here. And then superimposed on top of that are, in this case, water vapor absorption features showing up in the spectra of these worlds. Okay, direct imaging in reflected light. And so let's think about how the reflected light signature from this planet is going to scale. And so the first thing to remember is that we are looking at stellar light reflected off of this disk, and that stellar light is falling off as one on the orbital distance squared from the host star. The planet then presents a disk whose area scales as the planetary radius squared for collecting that light. And then on top of that, the fraction of that light collected that actually makes it to you, the observer, scales with the albedo of the planet. And so, lumping all of that together, you get that the planet-to-star flux ratio in reflected light should look like, should scale with the planetary albedo, should get larger with the planetary radius squared, and should fall off as 1 in the orbital distance squared. And then I have actually snuck in one additional parameter here, which is called the phase function. And so the planetary phase function just tells you about how the reflectivity changes as a function of phase. It's 1 at full phase when the planet is most bright, and it is 0 at new phase when the planet is unilluminated from your perspective, and has wavelength and phase-dependent structure in between those two extremes. Okay, so putting that expression front and center, what are things that we could hope to say about exoplanet atmospheres or biosignatures given a planet-to-star flux ratio spectrum in reflected light? You should be able to say something again about atmospheric opacity, which is going to affect the albedo primarily. You should be able to say something about surface reflectance, which again will affect the albedo. You should be able to say something about how the atmosphere and the surface scatter into different phases through this phase function. And if you observe that with polarized light, you can hope to get additional information about the surface and the composition of the clouds. You have information about the planet's size, and you have information about the orbital distance. And then what are things you could hope to infer given those quantities? So again, you could hope to say something about trace and bulk gas composition in the atmosphere. Hope to say something about atmospheric pressure here through Rayleigh scattering features or pressure broadening of molecular absorption features. And you might be able to say something about aerosols. And then combine surface reflectance with how the surface is scattering, again, maybe with polarized observations, say something about the composition of the surface. And again, here I'm going to point out that there are lots of potentials for degeneracies. A really easy one to spot is the radius orbital distance degeneracy. And so hopefully for a directly imaged exoplanet system, you've revisited it enough times to constrain the orbit such that this parameter is known before you try to do your spectroscopic analysis. But also you could see that the albedo and the planetary radius could kind of trade off, and that something that is high albedo and small could be about as bright as something that is low albedo and large, although there are ways of breaking that degeneracy. Just real quick, here is a faux reflected light observation of our home, shown as planet-to-star flux ratio as a function of wavelength from the near UV out into the near infrared, with some key features labeled, including the oxygen A band, strong biosignature, the UV ozone absorption feature, which is a very strong absorption feature in our planet spectrum. And then our spectrum is increasingly chewed up by water vapor bands as you head out into the near infrared. Something that I have swept under the rug and which provides an important additional angle to exoplanet atmospheric characterization is spectral resolution. And so here's a spectrum of our planet in the thermal infrared, done at 2 different spectral resolutions. Spectral resolution is just a way of describing how finely in wavelength you're sampling a spectrum. And so here's a spectrum that is sampled at every 10 to the minus 4 microns, so very finely sampled, which translates to a spectral resolving power of over 100,000 for those of you who are spectroscopists. And then here's a case where the wavelength bins are only 0.3 microns wide, which translates to a spectral resolving power of about 50. And so something that going to extremely high spectral resolution then opens up for you is the ability to spot Doppler shifts. And so here I have redshifted that emission spectrum ever so slightly due to, say, a few tens of kilometers per second motion of our planet. And so going to high spectral resolution can then open up avenues to go after Doppler shifts, which tell you something about velocities. And there are actually 2 different things that you can learn about exoplanet atmospheres from these Doppler shifts. So first would be the orbital motion of the planet itself should induce a Doppler shift in its spectrum. So you can say something about the orbit of the planet by observing Doppler shifted lines. But also, let's say you're observing a planet in transit. That planet is now moving transverse from your perspective, and so there is no radial velocity for a Doppler shift. But there are winds going on in that planet's atmosphere that could induce Doppler shifts, and so you could hope to constrain something about wind speeds in exoplanet atmospheres from these Doppler shifts if the wind speeds are rather high. The trick that is usually played is that when you go to extremely high resolution, you're spreading your photons out into lots of bins, which means that the signal to noise ratio of the planet spectrum is extremely degraded. And so you get your SNR back by integrating over wavelength by doing a cross correlation. So you compare the observation that you have to some template and say, how well do these two resemble one another? That integrates the wavelength dependence out and gives you back some stronger signal to noise. What's nice about the high resolution techniques is you don't need to separate the light of the planet from its host star. And so you have lots of photons that you're getting from your host star, and then sitting underneath that is a spectrum of your planet at high resolution that is Doppler shifting due to orbital motions, say. And so if you can gain sensitivity to these Doppler shifts, you don't care about the fact that there are tons and tons of stellar photons sitting on top of the stellar or the planetary spectrum. And then, of course, this is extremely well suited to ground-based facilities because of their large collecting area, which then enables them to go to extremely high spectral resolution. And so I will just show you one of the classic results of these high-resolution techniques from Broglie et al. 2012, published similar result at the same time from Rodler et al. 2012. And so this was for a hot Jupiter exoplanet, Tau Boötis b. This was a planet detected by radial velocity, but that is not transiting. And so if the planet is not transiting, you don't know the inclination of the planet's orbit, so you don't know the planet's mass. But what these authors were able to do was they took a high spectral resolution observation of the system, so that's combined starlight, and sitting underneath that starlight is the high resolution spectrum of the planet. They cross-correlated that with an opacity spectrum of carbon monoxide, which they expected to be present in the atmosphere of this exoplanet. And then they varied the bulk system velocity, so how fast the star is moving towards or away from us, as well as the radial velocity of the planet's orbit. And they got a strong detection for a good match between the CO template and the high resolution spectrum at a particular radial velocity of the planetary orbit and system velocity. And so what was amazing about this is the projected velocity of the planet's orbit combined with the orbital velocity that you get from radial velocity observations then allows you to infer the inclination of that planet's orbit that then gives you the mass of the planet. So this was a really impressive result coming out of using high spectral resolution techniques. Okay, so given a high resolution, or given a spectrum, how can you say something about the atmosphere? So let's play a game here. This is a spectrum that you have acquired, and you hand it to me, and you say, Ty, tell me something about this planet. And I squint at it, and I go, oh, Rayleigh scattering? And you go, tell me something physical and quantitative about that planet. And so if you want something physical and quantitative about that planet, you're into the realm of fitting physical models to observations. And you have a few options for how you can do this. You could ask me to produce a few spectral models of the planet that you then kind of by eye compare to this and squint and say, fits good enough, and publish it. And you got away with that if it were a decade ago in the exoplanet literature, but we have progressed since then. Another option would be to just run a super huge grid through parameter space of all kinds of atmospheric simulations of an exoplanet and compare those spectral simulations to these data using some metrics like chi-squared and find the ones that fit well to say something about that atmosphere. And with a bit more extra work, you can get actually quantitative about error bars there. Or you can do what is now very popular in the exoplanet literature. You can move on to Markov chain Monte Carlo. The latter two techniques here broadly fall underneath the umbrella of exoplanet retrieval. So I'm going to talk quickly about exoplanet retrieval and how that goes. And so here's a cartoon for how retrieval unfolds. I'm going to start in the top left, where you begin with some initial guess for the atmospheric state. Atmospheric state is just jargon for mixing ratios of species in the atmosphere, the temperature structure of the atmosphere, information about clouds in the atmosphere. You then pass that to a forward model, which is a fancy way of saying a radiative transfer model whose job it is to take the atmospheric state and produce for you a high resolution spectrum of that planet. Of course, you probably aren't observing that planet at high resolution. You're observing it through some telescope that degrades the information in some way. And so you need an instrument simulator to superimpose on top of that high resolution spectrum what the instrument does to that. And so you could use something like Natasha Batala's Pandexo simulator, which is up online and does James Webb and HSC. Our group maintains a direct imaging instrument simulator on our website. From that, you get a degraded spectrum. So now no longer a nice, pretty high resolution spectrum, but something that's blocky and chunky in wavelengths because you've degraded the spectral resolution. You then take that degraded spectrum and compare it to your observed spectrum to get some kind of fit metric. And so this could be just as easy as chi-squared. So comparing the simulation to the data and doing data minus model squared divided by the uncertainty on those observations squared to get a judge of how well you're fitting the observations. You can get increasingly more sophisticated in how you treat the likelihood of that model fitting the observations. And then given that information about how good that model fit the observations, you then move somewhere else in parameter space. And so this is called a sampling algorithm. So maybe you just changed the gravity and you got a slightly better fit by decreasing the gravity. And so your sampling algorithm says, well, let's continue trying decreasing the gravity to see if we can get the fit to be even better. And so I've been working on a way of trying to visualize this for you all. Spent an inordinate amount of time on this, mostly because I'm not good at Python and I insisted to try to do this in Python. So here are those data that you just handed to me, and I'm going to try to fit models to that to say something about the atmosphere. Let's say we knew the radius of the planet. Let's say we knew its gravity. Let's say we knew its orbital distance. And I decided that I only want to try to fit for a couple of parameters. I'm going to try to fit for the surface pressure of this world, and I'm going to try to fit for the mixing ratio of water vapor in the atmosphere of this world. Because maybe I'm squinting over here and I'm thinking, oh, maybe there could be some absorption happening out at the red here in the spectrum. So when the movie plays, you're going to see the Markov chain Monte Carlo tool trying out different surface pressures and water vapor mixing ratios to try to match these observations. Sitting here, you're going to see dots starting to pile up in this posterior distribution, where the dots are clustering or telling you where you are producing the best fits to the observations. Eventually, you'll start to see contours here that are 1 and 2 sigma contours. You can think about that as being like a mountain that's rising up out of this image. And then if you were to view that mountain along the y-axis or along the x-axis, you would get the marginal distributions. And so that just tells you what is the posterior distribution for water vapor when you integrate out all of the pressure effects, or what is the posterior distribution for water, surface pressure when you integrate out all of the water vapor effects. Okay, so let's hope this plays. It's going to speed up as time goes on, so it's trying different numbers. And what you should see is that it pretty quickly locks in on needing to decrease the surface pressure away from the initial guess. And then that doesn't change very much, but then it spends forever trying to figure out what the heck to do with water vapor. And so again, you can see that the marginal posterior distribution for pressure here is really getting quickly populated, whereas the water vapor one is kind of all over the place. I'll let that play for a few more seconds. And then I'm going to jump to what the final result looks like at the end of the movie. And so you see a really nice kind of Gaussian-esque distribution for how I constrain the surface pressure on that from those observations. And then a much more messy posterior distribution for water vapor that has this awful tail out to tiny numbers. You can see that at 1 sigma, it's pretty much consistent with there being no water vapor in the atmosphere. And you can see on the plot over here where I have in dark purple and in light purple have the 1 sigma and 2 sigma spread in the spectral fit to the observations, that at 1 sigma and at 2 sigma, you're pretty much consistent with being flat through the 950 nanometer water vapor band. So you do not get a good constraint on the atmospheric water vapor. Okay, so this is the entree for us to talk briefly about signal to noise ratio, which Aki wanted me to talk about. So this spectrum that you initially provided to me was actually at about an SNR of about 5 at V band. So if you take the signal at this wavelength and divide it by the size of the error bars, you get about 5. Well, what happens if we increase the SNR of those observations to 10? So notice that the error bars over here are now a factor of 2 smaller. Let's compare the posterior distributions for these two situations. And so now here are the SNR, here are the fits to the SNR 10 observations. Notice that the pressure fit is still good. It hasn't changed very much. But now our water vapor fit is actually quite nice. And to plus and minus 1 sigma is less than an order of magnitude, which is excellent by exoplanet standards. Usually we're pretty happy to get factors of 10 on gas mixing ratio constraints. So the question that I have is, why did the water vapor constraint get so much better while the pressure constraint did not improve very much? Think about that for a second. So what I'm going to do is go back to these two spectra. What I'm going to point out is that because we had many points across the Rayleigh scattering slope over here in the low SNR spectrum, we were resilient to the high noise shifting a couple of these points away from the smooth Rayleigh scattering slope. And so that meant that because we had lots of points through here, we could fit the Rayleigh scattering slope just fine, and we had a good pressure posterior. And that story doesn't change very much when he went to SNR 10. However, in the 950 nanometer water vapor band, we only have about 3 points through that band. And by random draw, one of those happened to be set pretty high. And that at SNR 5 gave the Markov chain Monte Carlo hell in trying to decide whether or not there's water vapor in that atmosphere. But when you move to SNR 10, now you can actually cleanly map out the water vapor band there. And so what that says to me is that your ability to constrain the atmosphere is really sensitive to SNR and spectral resolution in complex and nonlinear ways as a take-home message from that study. Okay, and then wrapping up, I want to talk about some future prospects for detecting exoplanet biosignatures. A plot that we have seen already from Vicki Meadows' review in 2017 discussing oxygen false positives. I know you all have kind of discussed this maybe to death, but the take-home message hopefully that you got from those discussions is that claiming a biosignature detection really is heavily reliant on context. You want to know what other gases are present in the atmosphere. You want to know what other gases are not present in that exoplanet's atmosphere. You want to know something about the system. You want to know about the planet's orbit. You want to know about the UV and high energy spectrum of the star. You need all of that information to be able to say something rich and detailed about a biosignature, potential biosignature detection. In the near future, one of our, if not our best prospect for detecting exoplanet biosignatures comes from the amazing transiting exoplanet system around TRAPPIST-1, which is thus far a 7-planet system, all small worlds, several of them, E, F, and G, in the host star's habitable zone. To date, our best attempts to get transit spectra and say something about the atmospheres have returned flat spectra. It could be that these are high mean molecular weight atmospheres, which makes the scale height small, which means that the features are small and we just can't get it with wide field camera 3, or it could be that there are hazes in these atmospheres. But never fear, James Webb is almost here. And so we all eagerly await what James Webb might be able to do for these amazing worlds. If you go into the literature, and I don't know if this is exhaustive, I tried to do my best to pull out all of the papers that have tried to say something about what James Webb might be able to do for temperate, rocky exoplanets. You get answers from kind of good luck, fat chance. Kevin Stevenson gave a talk at this year's Winter AAS, where if you observe every single possible TRAPPIST-1 transit for the potentially habitable worlds that you have available to you in the entire lifetime of James Webb, you might be able to get a CO2 detection if those worlds have an Earth-like atmosphere. To the other extreme, which was this is going to be easy peasy. And so given that those are all over the board, what this says to me is we really need to wait and see for what James Webb is going to deliver to us. And I also think observers are exceptionally clever people. They've proven this with HST. They're going to figure out all kinds of wonderful ways to use James Webb to increase sensitivity. And so it's great that we're trying to make predictions right now. Those predictions are super useful in trying to set thresholds for signatures that we want to go after. But we will have to wait and see what James Webb delivers to us. Okay. Scott is going to talk about this more. The 2020 Decadal Survey is coming up. There are several missions that are being sent to the 2020 Decadal Survey that have, as part of their main mission goals, doing exoplanet atmospheric characterization and hunting for biosignatures. One of these is the Origin Space Telescope, which would stand on the shoulders of James Webb. This is a thermal infrared telescope envisioned about 6 meters in diameter, super cooled, and would do secondary eclipse and transit observations of exoplanets from about 3 to 40 microns. Here's an example of the kinds of observations from their interim reports that they would hope to get. So this is an Earth-like exoplanet orbiting a late-type M dwarf at 4.2 parsecs, which is pretty close. James Webb is in blue, and then what OST would hope to do is in red. It gets better wavelength coverage, smaller error bars. They've indicated a number of species through here, so you might hope to be able to do oxygen, ozone, and methane in this Earth analog atmosphere to say something about atmospheric chemical disequilibrium and thus biosignature. 2 missions, HABEX and LUVOIR, thinking about exoplanet direct imaging. HABEX is thinking 4.3 meter monolith with an external occulter, i.e. star shade. LUVOIR is thinking 8 or 15 meters in space, segmented, and then with coronagraphs on board to do exoplanet direct imaging. Both would really like to return something that looks like this. This is from the HABEX interim report, an image of a planetary system that HABEX might hope to obtain. Several planets in the inner system here, and then a disk of debris disk external to those. And then for each of those, you would have a spectrum, so you could say something about its atmosphere. This would take about a week of observation time with HABEX, and would take between 20 and 150 times less observation integration time for LUVOIR, depending on the primary size. And then the hope is that in one of these systems, maybe you spot the pale blue dot with strong oxygen absorption in its spectrum, which is a strong indicator, at least for life for these planets around sun-like stars. Okay, and then I am just going to skip about 3 slides. And I'm just going to do it this way. Boop, 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 boop. And talk quickly about ground-based observations. So the ELT is going to be coming online in the mid-2020s. This is the ELT itself, the 30-meter telescope and the Giant Magellan telescope. And so all kinds of things are going to be possible, potentially with these, depending on their instrumentation, starting in the mid-2020s and on. They could be doing thermal infrared imaging of Earth around sun-like stars. And so this would be around 10 microns. There's an ozone absorption feature, 9.7 microns. So maybe they could detect ozone in these exoplanet atmospheres. They could be doing direct imaging of exo-Earths in the habitable zones of cool stars, again, going after biosignature, spectra and biosignature gases. And then something that is really going to be powerful for the ELTs is going to be high resolution techniques. Now, instead of talking about CO and water vapor in the atmospheres of hot Jupiter exoplanets, you could be talking about detecting oxygen in the atmosphere of Earth-like exoplanets using high spectral resolution techniques. And then if you combine that with high contrast imaging to beat down some of the starlight, as was discussed by Kawahara et al. 2014, you can even improve the situation some more. With that, I'm going to put up the questions that I sought to answer and thank a number of funders that I've had throughout the course of my doing this work, including the Sagan Fellowship Program, the NASA Astrobiology Institute, the Nexus for Exoplanet System Science, the NASA Exoplanets Research Program, and NASA Exobiology. So thanks to all of them too. Thank you.
Great. We have time for a couple of questions.
So you said that we can figure out things about like the surface properties or like the surface reflectance based on the albedo when you are thermally imaging the planet. But how massive the planet can be, like how massive the planet's atmosphere can be, till this approach will give you something about the, about the atmosphere, about the surface.
So I think that is going to be kind of a function of planet mass and of atmospheric mass, as you pointed out. So for an exovenus, you don't have any hope of being able to say something about surface reflectance, both because of the atmospheric hazes and because the atmosphere is so thick itself that you can't peer through it. And then as the planets move from the super-Earth regime to the mini-Neptune regime, which are kind of the ill-defined categories of worlds, and there could be some bleed between the two, eventually you get to the point where the envelope is so thick that, again, there may not even be a surface for you to peer at underneath there. It might just transition to weird phases of hydrogen or high-pressure ice phases and things like that. So depending on the thickness of the atmosphere and the type of the planet, there might not be anything that you could say about the surface. Something that Markov chain Monte Carlo can do for you is you can ask the tool, is there evidence in this spectrum for surface reflectance? And so you could actually ask, do I have sensitivity to the surface of this world?
Hi, I have a question about the retrieval method. So say if I have 2 sets of different physical assumptions going to 4 models, it's the sole metric, essentially chi-squared at the end, when I try to compare which one is more balanced.
Chi-squared does not have to be the sole metric. Ideally, the models that you're using to do this don't have different baseline assumptions. But as you point out, if 2 different groups use 2 different models that have different built-in assumptions, you're going to get 2 different sets of constraints given the same observation, which is problematic. One thing that you can do with Markov chain Monte Carlo, especially using Bayesian techniques, is you can ask of that tool, is there evidence in this spectrum for me needing to include this additional parameter for the atmosphere? Do I need to fit for gravity to match this spectrum, or am I giving the tool too many free parameters and thus overfitting my data? And so there are ways for you to try to hone in on what are the ideal set of parameters that I actually need to fit for when trying to explain this observation.
I have one naive question. There was one simulation of the spectra of Earth twin transiting the M star
Yes.
that you show. I'm wondering how did you simulate the cloud? And I saw the level between the spectra with the cloud and clear sky. They are not like too much different.
Yep.
Can I be naively say that we can just ignore the cloud for now, given the existing technology?
There we go. Okay. As was just pointed out, so the gray is clear sky, and then the blue would be adding the effects of clouds. So the way I added the effects of clouds is because this is Earth, I was able to go in and mine cloud locations for our planet and just put those into the transit spectrum. So this is a true Earth twin. If this were actually around an M5 dwarf, it would have different atmospheric circulation patterns and have different clouds on it. So that is not taken into account here. But because Earth's troposphere is only about 10 to 15 kilometers deep, and that's where all the weather is happening, the clouds only have a few windows in between these strong absorption bands where you could ever hope to affect the spectrum. And so the fact that our clouds are kind of constrained to be down close to the surface means that they really don't have that much of an effect on the spectrum. Hazes are a whole other story, which was as Jada was pointing out, those can occur much higher up in a planet's atmosphere, and thus have the effect, or can affect features that are poking up at 20, 30, 40 kilometers above the planetary surface, at least in this image.
Thank you.
Yep.
So, is there another question? If not, I would like to, oh, sorry, Aki would like, well, this is your session. You're trying to take from your own session here. So, so Aki is going next, but Aki would like to ask a question.
This plot in particular. So, okay, so if this was actually simulated around a G2 star, how much, where would refraction cut you off?
So if you were to put this around a sun-like star, a couple things would change. The overall transit depth scale here would change. And then the other thing that would happen is refraction becomes much more important for that observation. For those of you who are students who are going to lunch with me today, your homework is to explain to me why refraction matters so much more for the solar case. And that then cuts off your spectrum somewhere around 15 or 20 kilometers. And so you get a floor here from refraction much higher up in the atmosphere. And you have even less sensitivity to what's going on in the surface environment.
But the good news is the clouds don't matter because they're way below the refraction. Clouds become irrelevant when refraction kills your spectrum. Okay, all right, so I think we'll wrap up there. And